I'd like to thank the organisers for giving me the opportunity to speak here. Secondly, I thought it would be, given the context, given we've got a nice, big, varied audience, I thought it would be a nice moment for me to do a bit of advertising for my very talented, slightly younger collaborators, Davi Maximo and Valdo Paes Nunes, two very, very talented young mathematicians I'm very pleased to have worked with in the last few months. So what I'm going to present here is essentially work initiated by Davi and Valdo. They only brought me in when they started having difficulty with the technical parts. So most of the fun ideas, all of the fun ideas in fact, are essentially from Davi and Valdo. So what I'm going to talk about today is free boundary, minimal surfaces, and convex free manifolds. I'm going to explain briefly in a minute what those are. As you see, I tried to find some sort of, given that this is IMP, I tried to find a Mobius strip or a nice graphic of a Mobius strip to put in front of the talk, and the only thing I could find was that, but I thought it was pretty. Anyway, let's start by introducing the framework of the problem that we're going to be studying. So, what we study in our paper is a little bit more general, but I thought given that this is a lecture to present the subject, I thought I'd give a slightly more simple framework. So we start with omega. Omega is a smooth, bounded domain in R3 with smooth boundary. Then what we do is we give ourselves an abstract surface, S. S will be a compact surface with boundary. And what we're going to be studying are smooth embeddings, which we will call E. And these are mappings from S into omega with the property that they send the boundary of S into the boundary of omega. Now, I'll just remind you that if E is a mapping that sends S into omega, then E is said to be an immersion when dE, the derivative of E, is injective at all points. And E is said to be an embedding when, in addition, E is injective. But I'm sure you all know that. So, the objects that we're going to study, free boundary minimal surfaces. Now, a free boundary minimal surface is simply a minimal surface inside this ball which meets the boundary of the ball orthogonally. Now, before I go a little bit further, what I'm going to do is I'm going to give you some very, very simple examples, partly to illustrate the sort of objects that we're going to study, and partly because these examples actually play an important role at a key moment towards the end of the talk. So, the simplest example is the following. We give ourselves B in R3, a closed unit ball. So it looks like this. Now, we consider the case where our surface sigma, or S, according to this notation up here, is equal to the closed unit disk. And we look for free boundary minimal surfaces in the ball which are diffeomorphic to the disk. Now, most obvious ones, and I think the only ones, can't remember if this is actually the case, but probably is. The most obvious ones are the equatorial disks. So these will be the intersection of the ball with any linear subspace which passes through the origin. These are clearly minimal, totally geodesic, and they intersect the boundary orthogonally. Now, that's a very simple example of a free boundary minimal surface in the ball. Now, for technical reasons, throughout the rest of the talk, I'm actually going to be interested in oriented surfaces. So I'm going to differentiate between two surfaces which have different orientation. So when you're interested in oriented surfaces, the space, every equatorial disk inside the ball is uniquely defined by its upward pointing unit normal vector. And given that the space of unit vectors in R3 is equal to the sphere, what that means is that the space of all equatorial disks is going to be diffeomorphic to the sphere. So what that means, in the language that we're going to be using presently, is that the moduli space of these trivial solutions of these equatorial disks is two-dimensional, compact, and equal to the sphere. Now, let's consider a slightly more sophisticated example. Again, we're going to be interested in the unit ball with the standard Euclidean metric. But now we're going to be looking at the case where this surface S is an annulus. So S is equal to S1 times closed interval between -1 and 1. And we're now going to ask ourselves, what are the free boundary minimal surfaces which are diffeomorphic to the annulus? Well, we consider functions f lambda, parameterized by this positive real parameter lambda, which send r into r, given by a function which sends x into lambda times the hyperbolic cosine of x over lambda. It is that. I think it's that one. I hope it is, otherwise I'm going to look a bit stupid. Now, somebody tell me if I've chosen the wrong function. The graph of f lambda looks like this. And as everyone knows, the surface of revolution of f lambda about the x-axis is minimal. Secondly, if we take a look at the unit ball, well, start by looking at the unit circle. We know that there exists a unique parameter lambda such that f lambda meets the unit circle orthogonally. And when the graph of f lambda meets the unit circle orthogonally, what that means is that the surface of revolution meets the ball orthogonally along its boundary. So we have this unique parameter lambda such that the surface of revolution of the graph of this surface is a free boundary minimal surface in the ball. Now let's ask ourselves again, what is the moduli space of these surfaces? I'm going to call these surfaces actually critical catenoids. These are going to be important for us later. First thing to notice is that given the critical catenoid, there are two ways of orienting it. We can orient it so that the upward pointing normal points away from the axis of rotation. Or we can orient it such that the upward pointing normal points towards the axis of rotation. That's the first point. Second point is that given an orientation away from the axis or towards the axis, any critical catenoid is uniquely determined by its axis. So, and we know that the space of all axes in R3, that's just two-dimensional real projective space. So we know that given an orientation, the moduli space of critical catenoids with that orientation is diffeomorphic to real projective space. And since there are two possible orientations, what that means is the moduli space of all critical catenoids is diffeomorphic to two disjoint copies of RP2 of real projective space. So that's this moduli space of these relatively trivial free boundary minimal surfaces. So those are some two straightforward examples to warm us up and to give us an idea of what's going on. Now let's get on to the main theorem. The main theorem is a nice little application of degree theory, and it just tells us that if omega is strictly convex, smooth boundary, then there exists at least one free boundary minimal embedded annulus. Actually, the theorem that we have says a good bit more than that, but this is the version I want to present to you today. Now, I won't keep any secrets from you. The result is proven via a nice application of differential topological degree theory in infinite dimensions. So, before I explain how this degree theory works, I'm going to have to spend a few minutes explaining to you the construction that we use. Now, I have to say that the degree theory in its current form that we use here owes an awful lot to Harold Rosenberg, because basically Harold is the one who managed to understand what Brian White was doing and explain to me clearly what Brian White was doing, and otherwise I don't think I would have managed to understand it myself. But the current version that we use certainly owes an awful lot to Harold's influence. So, it starts as follows. We start off, we define a candidate space. Call it the candidate space because this is the space in which all the solutions will live. So we define it as follows. Let E tilde be the space of all smooth embeddings, send this surface S into omega. We're returning to the general case, so S can be any surface. And we suppose E sends a boundary of S into the boundary of omega. We let diff plus be the group of smooth orientation preserving diffeomorphisms of S, and we see that diff plus acts on E tilde, acts in the space of embeddings by reparametrization. So we simply quotient out by reparametrization, and we get this nice space E. E is the quotient space. It's a space of all. You can view it either as a space of all unparameterized embeddings, or you can view it as a space of all reparametrization equivalence classes of embeddings, as you prefer. So E is a space of unparameterized embeddings. This is a candidate space. This is a space in which we know the solutions will have to be found. Then we define the data space. So this is a data which defines problem. So we let G be the space of all Riemannian metrics over omega with two properties. One, G has positive Ricci curvature. Now, here I'm cheating a bit because if you remember, the Euclidean metric has zero Ricci curvature. It doesn't have positive Ricci curvature, so it's not actually going to live in this space. This is a minor detail that I don't really want to expand on in this talk. It's a very minor detail. G has positive Ricci curvature, and the boundary of omega is strictly convex with respect to G. So, we call G the data space, and we can also call metrics that live inside this data space admissible metrics. Now what we do is we look inside the Cartesian product of the data space. So we picture a graph very much like this. In our vertical axis, we place the candidate space, E, the set of all reparametrization equivalence classes of embeddings. In the horizontal axis, we place the data space, G, which is a set of all metrics. We now look at the Cartesian product of these two spaces, and we define Z. I chose Z because 0. Z is the set of all pairs EG, such that E is free boundary minimal with respect to the metric G. So, as we'll see presently, Z is actually the zero set of a functional, which is why I choose to call it Z. Then what we're going to do is you just look at the canonical projection pi onto the second factor. And basically, all of what we're doing reduces very simply to studying the differential topology of Z and of pi. The starting point is this recent nice little theorem of Fraser and Lee, which generalizes the earlier theorem of Choi and Schoen for embedded minimal surfaces inside compact Ricci positive manifolds. And this is that the mapping pi is a proper mapping. Now, why is this important to us? It's important to us for the following reason. Suppose let's just return briefly to the finite dimensional world. And suppose that we have a smooth mapping F, which sends one finite dimensional manifold into Y, which is another finite dimensional manifold of the same dimension. And let us suppose that this mapping is proper. Then we know that if X and Y are both orientable, then F has a well-defined z-valued degree. So that's the idea. We want to use this analogy with the finite dimensional world and do the same thing in the infinite dimensional world. Because we have this thing Z, and we want to pretend that Z is a manifold. We have this space G, and we want to pretend that G is a manifold. We want to pretend that Z and G both are the same dimension. We have this mapping pi, which is smooth, and we know now that pi is proper. So given these ideas and given this analogy, what we really want to do is we really want to show that pi, in analogy to what we have here, also has a well-defined z-valued degree. Now, why should the degree be important to us? Well, if we take a look at this picture here, and we take a look at some data point, G, here. Well, the set of points in the solution space, the set of points of Z, which lie above this data point, these correspond exactly to those embedded surfaces which are free boundary minimal with respect to this metric G. That is to say, pi minus 1G is simply equal to the set of free boundary minimal embeddings. At the same time, we know that what the degree counts is that the degree simply counts algebraically the number of points in this inverse image. So we know that if the degree of pi can be defined, then the degree of pi is simply equal to the algebraic number of elements in pi minus 1G, and this is equal to the number, counted algebraically, of elements of free boundary minimal surfaces for that metric. So if we can show in particular that this degree is non-zero, then we know that there has to exist a non-trivial quantity of free boundary minimal embeddings. That is to say, there has to exist at least one. So that's the strategy of the proof, and this is why, starting from this nice, straightforward differential geometric question, we now move entirely into the world of infinite dimensional differential topology. So, the first step that we want to do then is we want to understand in what sense this space Z can be considered a manifold. So, we have a look again at the definition of the space Z. Z is the space of all free boundary minimal surfaces. So what we can do is we can write that as a zero set of functional. So we take some point, e.g., inside this Cartesian product. And we define two functionals. First functional that we define, we'll call it big theta, capital theta. This is a function that sends delta sigma into R and measures the angle E sigma makes with delta omega with respect to the metric G at each point. So omega looks like this. Sigma here is living inside omega. This is the image of S under the action of E. Actually, I'll draw it side on. It's easier to understand that way. So the image of the embedding looks like that in the ball. Here, at the boundary point, we have the tangent space to the image of the embedding. And we have the tangent space to the boundary of omega. And these make an angle theta. Now, for every point in the boundary, we can define this angle theta. And this function, capital theta, then, is a function which at each point P gives you that angle theta. Well, actually what you want is theta minus pi over 2. You want the angle between the between this plane and the normal to this. But that's not important. We then let H be the normal mean curvature functional over the embedding. And it then follows that Z, the zero set, a set of all free boundary minimal embeddings, is simply the set of all points where these two functionals, theta and H, vanish. It's as simple as that. Well, technically theta is equal to pi over 2, but just subtract pi over 2 and everything is fine. So already we can see that Z is a zero set of a functional. So what we want to do then is we want to apply the immersion theorem to show that Z is some sort of manifold. And the trick behind that is the following. It's actually a nice observation that we were quite fortunate to make. There are two different approaches you could do. What you could do is you could restrict attention. Our first attack at this problem was to restrict attention to those surfaces, the space of those surfaces which meet the boundary orthogonally. And then once we restrict attention to that space, you look at the Jacobi operator for a mean curvature, which you know is a generalized Laplacian, which you know is elliptic, and therefore allows you to apply Fredholm theory. But that was incredibly complicated. What makes it much, much simpler was the realization that we made some weeks into working on this, that this pair, JH, J theta, actually defines a Fredholm mapping from C infinity sigma into C infinity sigma times C infinity delta sigma of Fredholm index equal to 0. So once you make that observation, actually the formal construction of the degree theory that we're wanting to study here is not too different from other degree theories that we've already done. So if we have a data point, e.g., in this set Z, we will say that this data point is non-degenerate whenever this Jacobi operator J is invertible. So the Jacobi operator, normally when you look at minimal surfaces, you look at the Jacobi operator of mean curvature. This time what we're looking at is the Jacobi operator of this pair, mean curvature plus boundary angle. Now, what you do then is we have that this Jacobi operator is Fredholm of index 0. You then prove a technical and rather pretty surjectivity result. And once you have that surjectivity result, that allows you to say that Z, which is then going to be the zero set of this nice smooth functional, is actually an infinite dimensional manifold. There are different ways you can work it. For people who like technical stuff, you could work in the Frechet category, apply the Nash-Moser theorem, and then you would show that Z is a smooth, tame Frechet manifold. Or you could work in the Banach category, apply the inverse function theorem for Banach manifolds, and show that Z is a Banach manifold. You do what you like. There are various different ways of interpreting Z as an infinite dimensional manifold. But the point is, it's an infinite dimensional manifold. And once you've got there, well, then you just apply the Sard-Smale theorem in the usual way, and you get this theorem which tells you that there is an open dense subset G0. Remember, G is the space of all metrics, so there's an open dense subset G0 contained in G, such that for all these metrics, number one, the inverse image of G is finite set. Number two, every element of the inverse image of G is non-degenerate. And given then that you've got a finite number of non-degenerate elements, you can then define an integer-valued degree by looking at the Morse index of every solution. So we then define the degree like this. The degree of the projection pi is equal to the sum over all elements in the inverse image of G for a generic element G of -1 to the power of the index. And we call this a mapping degree of pi. So very briefly, I haven't actually defined the index. So let's just have a look at that. Remember that the Jacobi operator then is this pair JH, J theta. Okay? What we can do is we have a look at all smooth functions over S. Normally when we're doing differential geometry, we're used to looking at smooth functions, or smooth functions over a manifold without boundary, or smooth functions over a manifold with boundary which vanish along the boundary. So we're going to look at something a little bit different. We're going to look at C infinity theta S, and these are the set of all smooth functions phi, such that J theta phi is equal to 0. We start by looking at the kernel. Now, this is what is known as a Robin boundary condition. We then have a look at JH. Now, JH is then a second order linear partial differential operator which sends C theta infinity S into C infinity S. And you can show that the restriction of JH to this space is Fredholm of index 0, self-adjoint, so it's elliptic, so it's a nice discrete spectrum, and you can show that the spectrum is bounded above or below, depending on your choice of orientation. So if you have a look then at the spectrum of JH, then you know that the spectrum of JH is a discrete subset. I'll choose it this way. And then it goes off to infinity in this direction. It's a discrete subset of C, which is bounded below by some constant B. And we know, moreover, that all the eigenvalues have finite multiplicity. So, the index of the solution, E, is simply defined to be equal to the index of this JH. Okay? And the index is simply equal to the sum over all eigenvalues lambda, which are negative, of the multiplicity of lambda. That is, it's simply the Morse index of this operator. The Morse index is simply the number of strictly negative real eigenvalues counted with multiplicity, and that allows us to define the index of any free boundary minimal surface, and then that gives us the mapping degree for pi. So we now have the mapping degree. This is very well. So we know the thing exists, but we still haven't calculated it. So in order to calculate it, we need a slightly more subtle concept, which is that of the local degree. And the local degree works like this. How am I for time?
About 10 minutes.
10 minutes, okay. So the local degree works like this. Again, we consider our Cartesian product of E with G, candidate space up here, data space down there. We look at Z. Looks like this. Now what we're going to do is we take an open subset of E, omega, here. Sorry, we take a data point, G0. So G0 is here. Pi minus 1 G0 is this, and this up here. And then what we do is we look at an open set omega contained in E with the property that the boundary of omega does not meet the inverse image of G. So the boundary of omega doesn't meet this red set. What can we do in these circumstances? Well, the first thing we can say, just applying properness, this isn't difficult, is you can show that the boundary of omega, in fact, will not meet Z even over a neighborhood of G0. That is to say, we can take a neighborhood U of G0 in the space of all metrics, and we look above U, and we see that Z inside U part of Z which is living above U does not intersect the boundary of omega. Okay? Now, so that's proposition. Now, what does that mean? That means, in fact, if you just restrict attention then to the intersection of Z with omega times U, then in fact the restriction of pi again to a proper map. So what that means, in fact, is you can define a degree for the restriction of pi to this smaller chunk of Z. And that is what we call the local degree. And we're going to denote this by deg, the degree of pi restricted to omega. Okay? So we define the local degree in exactly the same way as we define the global degree. And it's fairly easy to see that if omega 1 and omega 2 are disjoint, open subsets of E, such that the inverse image of G0 is contained in the union of omega 1 with omega 2, it's not difficult to see that the degree of this projection pi is equal to the local degree of pi over omega 1 plus the local degree of pi over omega 2. So, now using local degrees, we can conclude. We go back to so remember, we were interested in annuli. So we now take G0 to be the Euclidean metric. As I say, I know that the Euclidean metric is not Ricci positive. This is a technical bit that I don't really want to explain in this talk. It's not very important. It's not a serious problem. Let G0 be the Euclidean metric. So, and we have a look at pi minus 1 G0. So pi minus 1 G0 is this part of the solution space that lives above G0. And we know, we already studied this at the beginning of this lecture, that pi minus 1 G0 contains this family Z1 of extremal catenoids. And we know this family is a compact, two-dimensional family of embedded surfaces. And as I already showed you earlier on at the beginning of the lecture, this family is diffeomorphic to two disjoint copies of R2. Not only can we show that, but you can also show that for every element, E, for every embedding E in this family, the kernel of this Jacobi operator, JH, J theta, is two-dimensional. This is really nice, because the kernel of every element of this family is equal to the dimension of the family. Now remember, if you have a non-degenerate solution, if you have a non-degenerate minimal surface, and here non-degenerate means that the Jacobi operator is invertible, then you know that for any perturbation of the metric, sufficiently small perturbation of the metric, you can perturb the surface to get another surface which is minimal for the perturbed metric. And this generalizes to the case of smooth families. You can think of a single solution, a non-degenerate solution, as a non-degenerate zero-dimensional family. If you have a two-dimensional family, the condition for being non-degenerate is that the dimension of the kernel of the Jacobi operator is equal to the dimension of the kernel of the family. So what that means there is that we have this non-degenerate family inside the solution space, which is diffeomorphic to two copies of RP2. When if we were to perturb the metric, because of the non-degeneracy, we can perturb this family in such a fashion that it actually breaks up into a finite number of free boundary minimal surfaces. And we can even count algebraically this number of free boundary minimal surfaces, and we can show that it's equal to the Euler characteristic of the moduli space of solutions. And we know that the moduli space of these solutions was two copies of RP2. So the Euler characteristic is, the Euler characteristic is equal to 2. Because RP1 has Euler characteristic 2. I think. Anyway, second interesting property is that Z1 is isolated inside the solution space. This is also a property of non-degeneracy. So what that means then is what we can do is we can imagine that this red set here is Z1, and we imagine this is everything else. And we let omega 1 then be a neighborhood of Z1. We let omega 2 be a neighborhood of everything else. And we look at the local degree in omega 1, the local degree in omega 2. So, we do this, as I say. We take omega 1, omega 2, and E, such that Z1, so Z1 is the space of all critical catenoids, is contained in omega 1, and everything else, all the other solutions that we don't know about, they're contained in omega 2. And the intersection of these two open sets is 0. Then, as I said, using this perturbation argument, we know that the local degree inside omega 1 is equal to 2. And using a very nice symmetry argument, which I do not have the time, no? Do I? I have a few minutes. Oh, right, good. Using a very nice symmetry argument, which goes back to work of Brian White, you can show that the contribution to the degree of everything else is equal to 0. Now, before I explain where that comes from, just observe that what this means is that the degree is non-zero, which means that there exist solutions, and that gives us our theorem, that there exists a non-trivial and free boundary minimal embedded catenoid. So, let's just have a look at the symmetry argument, which is very, very pretty. So, for V, a unit vector in R3, and for n positive integer, we define R V n to be the rotation clockwise of 2 pi over n degrees radians about V in R3. And now what we do is we look at we imagine we have a free boundary minimal embedding which isn't a surface of revolution. And we look at what happens when we rotate it about some vector. So we have our free boundary minimal embedding, maybe looks like that. What you can show is that, let's call it sigma, is that there exists some number n bigger than 0, such that for all sigma, not surfaces of revolution, so for all free boundary minimal sigma, which are not surfaces of revolution, for all unit vectors V, and for all n bigger than or equal to n, the rotation about the vector V by an angle of 2 pi over n of sigma is always going to be different to sigma. Okay? In particular, what that means is if n is prime, then that gives you p many disjoint copies of sigma. So what we do is we can arrange things. We perturb the metric G. So we choose any number p. Let p be some prime bigger than n. And choose any vector v. Choose your favorite vector. And what we can do is we can perturb the metric G in such a manner that it's non-degenerate, and in such a manner that is actually preserved by rotation of angle 2 pi over p about this vector v. So what that means in particular, this reminds me of Etienne's talk yesterday, the solutions aren't symmetric, but the space of solutions is symmetric. The space of solutions is going to be invariant by rotation around this vector v. So what that means is going to be invariant, by rotation of 2 pi over p. Okay? So what that means, in fact, is that we have an action of the group of order p, so the group generated by this rotation, on the space of solutions. So the space of solutions which are not catenoids actually breaks up into a space of orbits of the group generated by R VP. So, schematically, we have the following. We have space of all embeddings here. We have those solutions which are critical catenoids. We don't worry about them because we've already counted them. Then, we've got a neighborhood of these things, and outside we have all other possible solutions. We've perturbed the metric such that this set of all other possible solutions is discrete. And we now know, because G prime is invariant by this mapping, the space of all other possible solutions is also invariant by this mapping. And we know from this result here that all orbits are non-trivial. So, what we have then is we might have one non-trivial orbit here, another here, another here, another here, and another here. Okay? So what that means then is that the number of solutions, even counted algebraically, is going to have to be a multiple of p. Thus, the degree of pi restricted to omega 2 is equal to p times k for some integer k. Okay? And this is true for all large p. And because it's true for all large p, and because the degree is integer valued, that means it must be equal to 0. Notice, and this is a nice point, is that for this to work, you need an integer valued degree. If you just had a z2 valued degree, then 1 is a multiple of every odd prime number. So what this reasoning would show is that your degree is a multiple of every sufficiently large prime number, and that doesn't tell you anything. That only tells you something when the degree is integer value. So anyway, that's the nice symmetry argument, which goes back to an idea of Brian White from the 1980s. It's very pretty. And that allows you to show that the contribution to the degree of all solutions which are not critical catenoids is equal to 0. So that the degree is equal to 2, so sum of these two things, and then you have solutions. Which leads me to add that actually reminds us of a very nice conjecture which is still open. We all know that the Lawson conjecture was recently proven by Brendel in February, I think. And there is also the Lawson conjecture there's an analogous Lawson conjecture for annuli in the unit ball in R3, which is to say, are the critical catenoids the only free boundary embedded annuli in R3? And that's a nice problem, totally analogous to the Lawson conjecture and still perfectly open. And if that were to be shown, then you wouldn't need this nice symmetry argument to show that the contribution to the degree of all other solutions is equal to 0. No. Thank you very much for listening.